Good morning, everybody. It's time again for quantitative big imaging, and I hope you had a good week and also that you could do some of the exercises I gave you for last week. Let's start with the lectures, and here are the slides. It should be in this one. Do you see my slides? Please a thumbs up or something. I hope this is the right one. Yep, good, great, thank you. So today I'm going to talk about image enhancement, which is one of the first steps that you do when you come across some images. And that is, there are a couple of things that we have to consider. And one is that our images are not perfect. Then we have several filters, and then the next thing is I'm going to talk about is how to evaluate how well we did with our filters. And measurements are rarely perfect. And also this slide I see is very tiny, but in principle, what you have is you get an image, or you actually have a sample which you measure, and you expect the image to be pretty nice, so sharp and clear, no problem. Unfortunately, it's not the case because we have some blurring in the system, and we also have some noise added, and on top of that we have artifacts. So in the end, you will get an image which doesn't look very convincing for many. Still, this is what you need to work with when you got your images from the experiment. So let's see what we can do with it. And there are, first of all, the noise and artifacts. In generally, it's some kind of unwanted information in the signal. Normally, what we are talking about is rather random contributions that obscure the image information. So if we look at some different noise types, we have, first of all, spatially uncorrelated noise, which means the noise signal is not depending on its surroundings. Then we have event noise, which is kind of an outlier noise. And in this example, we have salt and pepper. And then we have structured noise, which actually is spatially correlated because you have dependencies from pixel to pixel. And the little code you see here is different types of random generators and how to create these spots. And this was a big one. Let's see if I can bring it up. No, I can't. Then I actually need to rescale it, I think. That was not so nice, this one. Let's see if I can, no, I can't like this. Okay. Let's just change the size. Something like 10 and 6 should probably be good. No, it wasn't. I see. Like this in that case. It's not meant to show up. So let's just leave the notebook for a little moment. And then we can see here are some examples of Gaussian distributions with different average values. So that's the center of these distributions. And then we also have different standard deviations, which sets the width of this signal. And just get back again to the slides. So another type is Poisson noise, which is also spatially uncorrelated, but this time it's a multiplicative noise, which means it depends on the signal strength. And the signal distribution of the Poisson is, as you can see here, a little bit skewed. And in particular, if you have few events, it's more skewed than if you have many events. This is actually the one that you will see in reality in many imaging experiments, because what we are seeing is photons or neutrons or any kind of event coming in, and they come in with some rate. And this rate is given by, rate is describing the shape and the noise strength of the Poisson distribution. If we compare what it looks like, the different noise types, so we have Gaussian noise and we have Poisson noise, you can see that Gaussian noise here is nicely adding on, and you have the same noise amplitude no matter what the amplitude of the signal is. And you can also see this when I extract just the noise. On the other hand, if you look at Poisson noise, you can see that for greater amplitude you have of the signal, you also have much greater amplitude of the noise than if you have lower signal amplitude. And if you look at this extract, you can also see that the envelope of this curve is that it's pretty wide amplitude in this part and much less amplitude in this part. And then we have different noise models based on events coming in or some kind of thresholding. So it's an outlier type of noise, so salt and pepper. It happens that you have some kind of extra interaction that produces these outliers. Could also be that you have detector faults. Normally it's single pixels, but it can also be, for example, if a gamma photon is hitting the detector directly, then you would get a little blowout or flare covering several pixels. In this case, I have set a 2-level salt and pepper. So if we have values from uniform distribution, which are less than the threshold, then you set -1. If you have it within the safe boundary, it's a 0. And then if you are above a second threshold, you would have a 1. And the noise fraction is the sum of these two thresholds. And this is what it can look like if you have 1% lambda 1 and 1% lambda 2. Then you have spots spread out. But anyway, it's about 2% of the pixels are affected by this noise. If we then increase it to 10% in total, you see that you start looking like some kind of snowstorm. And if you go up to 20%, well, it looks like lost signal on the TV. So that's pretty much salt and pepper noise, and you can still work with it, but it's not fun anymore. An important quantity when you're talking about noise is we actually want to measure how much noise we have in the images. And typically the first go-to metric is the signal to noise ratio, which is the same as the average of the signal divided by the standard deviation of the signal. And this gives you a pretty good metric about how strong the noise is. Important though is to look at where you do the measurement of this signal to noise ratio, because if you have fluctuations, gradients, or even structures in the image, then the measurement will be skewed. So what you need to do is to locate an area, for example, out in this region, which you mark up as the place where you measure the signal to noise ratio. You can also see that if you would measure in this area, you would get a different signal to noise ratio. And even in this area, you would get yet another signal to noise ratio. So it's important that you do this outside of the sample to get the open beam signal to noise ratio. For the Poisson distribution, the signal to noise ratio is directly coupled to the number of events that you capture. And the average value of a Poisson distribution is actually the number of events. And then the standard deviation, or actually variance, is the same value. And the standard deviation is just a square root of it. So we get number of events divided by number of events square root. And then what we get as signal to noise ratio for the Poisson variable is square root of n. And you can see here in this example where I plotted different exposure times and measured the signal to noise ratio. You can see that this was acquired at 50 milliseconds and this one was at 10 seconds. And you can see there is a great difference. Exposure time is an important thing here. And it's actually not only that, but it's, as I say, the number of captured events. It can be, there are different ways of improving the signal to noise ratio. One is by changing the exposure time. If we have longer time that we capture the photons or neutrons or whatever information you capture, then of course you get more, and that's a way to improve the signal to noise ratio. Another thing is to change the pixel size. So if you have a larger area where you capture your events, you will also get more, of course, and that also improves the signal to noise ratio. Another thing is to also increase the flux. This is limited possible because if you have a kind of source, it's usually set to a standard, or it has at least a maximum what you can get out of it. So you can't improve much by pushing the source. When you start working with random numbers, which you are going to do when you do analysis of how good your methods are working, there are a couple of supporting functions in Python, in particular in NumPy. And here you can see that the Gauss random field, where you have an average value, a sigma, and you can also say how large should the signal be. So this would be that you set rows and columns of the image you want to create with the Gaussian noise. The uniform noise works the same, and Poisson is a little bit different. There you actually have to provide the image that drives to get this signal. Statistics to compute it, of course, you can calculate the sums yourself, but there are actually in NumPy also the mean, variance, and standard deviation. On top of that, you can also get min and max values from the signal, and median value and rank can also be extracted from NumPy. So you don't have to implement these functions yourself. It's just calling them from NumPy. So now we have seen that we have noise, we have artifacts. So what are we going to do with these problems? So we have filters, and in principle, going very general, a filter is some kind of processing unit that enhances the wanted information, possibly, or at least maintains it, and it suppresses the unwanted information. And this sounds good, but it's not as easy as you think. And in particular, you will see that usually when you apply a filter, there is some change to the relevant information too. So you should try to tune a filter in a way that you remove as much as possible that you want to remove and maintain as much as possible of what you want to keep. And there are different filter characteristics, and they depend on which information they want to suppress or amplify. And Typically, we have the low-pass filter, which enhances or maintains the slow changes in the image. And the rapid changes, they are suppressed from this. So if you look at this image here, then I have actually two basic signals in it. One is rapid changes, and the other one is a slow change. And after the low-pass filter, it should come out something like this, ideally. But usually with the different, depending on the filter type, it doesn't do exactly like this. The other type is the direct opposite, so it enhances the rapid changes, and the slow changes are suppressed. And of course, we get this grid of tiny dots instead. The basic filters we are working with are the first you take when you start playing with the data. And these are the linear filters, and they are based on the mathematical operation convolution, described like this. So it's actually, in the continuous case, it's an integral over the kernel and over the image. When we come to images, we are, as you know from last lecture, we actually have a discrete grid. So this integral is changing into a sum instead. And now we're going to look at different convolution kernels to produce a low-pass effect. And the first two that you will encounter in any literature and also in any software as well are the mean filter, also called the box filter, and the Gauss filter. In the mean filter, you take the neighborhood and just sum all of the pixels. In this case, I have a 5 by 5 neighborhood, and this would be the central pixel, and then it just sums all the 25 pixels in the neighborhood and divide it by 25, and then you get the filter value. The Gauss filter is a little bit more complicated because then the positions in the kernel, they have different weights. So you have to multiply by this weight before you sum. And these filters are typically used to suppress the noise and artifacts. And if we look at what happens when we have different signal to noise ratio and also different filter kernels. Here in this case, I'm using the Gauss filter. And again, I think I need to change here a little bit because this is way too big. Yeah, a little bit better. So here we can see some filtered images where you have the clean image here and you apply different width of the Gauss filter. So this is essentially no filter at all. This is the width 1 and width 3. You can see that there is some slight blurring between this and this one and an obvious blurring in this one. So this is actually what's happening to the clean signal in when you apply a Gauss filter or actually any convolution filter with low pass characteristics. And if you then decrease the signal to noise ratio, you see the image is getting noisy. So we have signal to noise ratio 10 here and 5 and 2. And you can see that the image is getting noisier and noisier. And if we now apply the different filters, you can see that actually it's improved pretty good. You lose maybe a little bit here in the bone structures, but still it looks decent. If you have lower signal to noise ratio, you start seeing some kind of blobby, patchy structures, and that's actually the summing up of these noise spots. And if you go to signal to noise ratio 2, it's easier to see the contour, but it's not so easy to work with anyway. Going for the wider kernel, you can see that there is not so much difference between signal to noise ratio 10 and 5, visually, there are differences. But if you go to signal to noise ratio 2, you can see that there is a clear improvement. You can actually now would be able to distinguish that there are a background and an object, but and the computer would also be able to segment this. But you can also see that the structures, they are completely lost. You see that there is an eye, if you know it, possibly an arm, but you can't see the details that you had up here in the bone. So it depends on what you need to do with the data afterwards, how strong you are allowed to filter. The convolution itself, it's computed like this. So you take an extract here. I have some pixel values and we take them out, sum them. And in this case, it's a box filter. So we divide it by 9 and place this 3.7 on this spot. And then we take this kernel and move it to the next position and compute the same value. And you just go point by point and do this. Sounds like a routine task, and it is actually. So you don't have to implement your own convolution unless you find pleasure in doing so. Because these functions, they are actually available already as functions in different packages. One thing is, as you can see, we have to make a lot of multiplications and additions. And in some cases, we can actually use some properties of the convolution. And that is that you can split it into smaller pieces. So the commutative and associative laws, they actually apply to convolution as well, because they are based essentially on addition and multiplication, or weighting in. And that's why you can see here that you can rearrange the variables in different ways. You can even switch them in the order. And that is something we can use for several of the common kernels. So the box filter can actually be divided into one vertical convolution and one horizontal convolution. The Gauss filter, even so, you can also split it in, because these two components, they are independent in the directions. So you can actually do convolution in X direction and in Y direction as 2 steps. Now you may ask yourself, oh, why should we mess around with this math? But there is a point. If you look down here, you can see that if you have a 3x3 kernel, that would be 9 multiplications and 8 additions. But if you do the separable way, then you would only have 6 multiplications and 4 additions. Slight gain, but there is a gain. If you do it in 3D, you would have 27 multiplications and 26 additions. But on the other hand, if you have done it the separable way, you would only have 9 multiplications and 6 additions. And here you may see there is a benefit in it. And if you go to even larger kernels, which is pretty common when you do Gauss filters, it's not unusual. You go to maybe 7x7 sized kernels to get the nice shape of a wider Gauss filter. So with that, you will have a great gain. And this is the reason why I mentioned this. No, not yet. Okay. Just one thing more about doing these separable filters is that it's not only the operations themselves, but there is some kind of overhead when you call a function twice compared to calling it once. And sometimes there is a balance between if it's worth doing a separable filter or not. Also, the other thing is there is a numerical deviation between the case when you have done the separable and the full kernel. And if you use double precision, it's usually not visible, but if you use single precision, you may see differences, but it's marginal, but still there are differences. So let's go over to the median filter, which is not a linear filter, but anyway, it has low pass features. And here, what you do is you take all the pixels from the neighborhood, you sort them, and you take the central value, and that is what you place here. This is a very popular filter. And in particular, you can see that if you have spotty images, here I added pretty many spots, the Gauss filter would give you somewhat larger spots, and slightly suppressed, but they would still be present. If you use the median filter instead on the spotty image, then you can see that most of the spots, they are gone. You have a pretty nice sharp edge, and well, the grasshopper looks much better than before. If you do add Gaussian noise instead, then you can see that the Gauss filter is doing its suppression work, but actually that the median filter is doing, in this case, a less good job. So it depends on which kind of noise you have in the data. And this is something you have to get a feeling of, which kind of filter you need to apply in order to get the best filter effect. Sometimes you need actually to do a combination of the two, that you do some median filtering to get rid of outliers, and afterwards you do some Gauss filter to remove the other noise in the image. One example where we can use this is for spot cleaning. And you can see here we have an image. In this image there are some spots, and those are very annoying when you do tomography because they introduce line artifacts. So a single spot gives a long line across the image. So we want to really get rid of these spots. The number of spots in the images varies, but and also in amount and the size and so on. And there are different ways of getting rid of them. We have already mentioned them. One would be to do a low pass filter. The other one would be to try a medium filter. And a little bit more advanced procedure would be to first detect the spots and then replace them with something that is suitable. And here is an algorithm doing so. So what this algorithm is doing is to take the original image. It does a median filter. You can see that it's essentially no spots anymore. And then you subtract that and take the absolute. And you can see that from this, you get an image which only contains the spot instead. So in principle, what we have done is a high pass filter because we get the small outliers. And in this, we now send them into some thresholding to produce the replacement. So if they are less, if the threshold is less than the outlier, then we should replace it by the median value. And this would be the replacement information. And if the image value or the detection image value here is less than the threshold, then we have just normal background, and then we should take that instead. Then we sum these two and we get a cleaned image. And here the n is the size of the median filter, and here is the threshold level. And this is actually something that works pretty good. And if we compare what it looks like after applying this filter, is that we have our spotty original. If you do a box filter, you can see that it's actually, well, reducing the impact, but actually it's smearing it out. So it's not really useful in that sense. If we apply the median filter, you can see, yay, we got rid of the spots, but you can also see that there are many finer details in the image that are lost with this. And if we apply the cleaning algorithm, you can see that we get rid of the spots, but also that all the other structures in the image, they are actually maintained. Looking at the differences we have here, you can see that there is a lot of background that is removed. Even you can see structures from the image, which is really bad. Medium filter has less structures, but still it also takes some of the noise. And finally, we have this cleaning algorithm, which mainly just takes all the spots and nothing else. For those of you who work with ImageJ, there are two ways of removing outliers, and they're called despeckle and remove outliers. Never use despeckle, because that one is just a plain median, and we don't want that. So then there is another one called remove outliers, and that is essentially the algorithm that I described right now. So you have to set some kind of window width, and you have to set a threshold level. And then it works in a similar way that I showed you. Now we have only been talking about low-pass filters to remove noise. Then there is the other type, which is high-pass filter. And now we are looking at enhancing rapid changes in the image. And rapid changes is when you go from background into an object, then you have an edge. This rapid change is what we want to enhance, and that can be done using the high-pass filter. And there are different types of high-pass filters. The gradients, the very simple one, is just taking pixel minus its neighbor, dividing by 2, and then you have the very basic gradient. This one has the disadvantage that it shifts the data by 1 pixel. So what is normally done is that you insert a 0 in the middle, and with that you now have a centered gradient. Then there are different performance depending on how you implement this gradient kernel. And this one has proven to be the one that produces the best gradient signal, and is also giving you the best orientations afterwards. The Laplacian is another one that is very popular. Then you have some positive values around a larger negative value, which is actually the sum of the neighbors. And another one which is very popular for edge detection is a Sobel filter, which is the absolute gradient, or the gradient amplitude, sorry. And this is computed like this. So essentially you take 2 times these 2 guys here, and then you place them in here. One thing I can mention also here is that now I showed you the gradient in the X direction. If you want the Y direction, then you need to actually place these number rows, columns. You have to place them, of course, horizontally instead, and put the zeros in between. Then you would get the oh, sorry. That was the wrong one. It should be Y. So, and then you get the gradient in the Y direction instead. So this is the way how so you need actually 2 kernels to compute the 2 gradients. Doing it in 3D is of course also possible, but then you would have a little cube as a filter kernel instead. Looking at what the 2 gradients look like, we have the vertical edges and we have the horizontal edges. So now we actually get dx and dy. So we have this original image, and we apply the vertical edge detection. And you can see here that you have a lot of small vertical lines for all these grid pieces here. And this region is a little bit more complicated. But what you also can see is that here you have a negative value, and here you have a positive value. So with this gradient, we can actually see if we are going through a rise or a fall, a rising or falling edge in the image. So this would correspond, to this area here, or to this one. And we can see that one is going, so it's always calculating from the left. So rising up into the material. So then we have some material, and then it goes down again into the air. For the horizontal lines, same thing. We also can see that it's going from top to bottom. So you have first positive edges. No, so we have rising edges and we have falling edges. So these are the two types. Then we can also look into more complicated filters. And in the package scikit image, you have already these filters defined. So you have Laplace and Sobel already implemented. And looking what they look like, we can see that the Laplacian produces positive and negative values. So you will have, when you come to an edge, actually no matter which direction, you would have, let's see, yeah, I can do it. You have something like, no, wrong way. Let's see. It was first going down and then up and going like this. And this you have for all the edges. And that is what you see here now. So it's getting dark and then it's getting bright. If you look at the Sobel, it doesn't have this. It only gives you a little bump where you have an edge. So that would be, for example, on this spot here. And that would be here, for example. And depending on what your algorithm is doing for detecting edges afterwards, sometimes the Sobel option is good, sometimes the Laplacian. So that is actually what you can, you have to choose which kind of filter you need to work with for this. Another one, importance of all these convolution filters is that they are very popular in machine learning. There is a large class of image recognition and detection filters, machine learning networks, which are based on convolution. And when you do the training of these networks, you actually do you configure in the training, you configure the different shapes of the filter kernels. And then afterwards, by running it through the whole weighting here, you can afterwards get some conclusions. In this case, it's an example from NVIDIA, where you can get the output signals that it's a sine, and then you can say which number this sine actually represents. So in this case, it came in the speed sine 60, and it actually answers that you got a 60 and also that it is a sine. Because sometimes with machine learning, if it's giving some data, it tries to say that, well, no matter what, this looks like a 60 sine, but it's a cat. The algorithm doesn't care. It just gives the one that is most probable. Therefore, you also have this detection that it's actually a sine and not something else. And with that, I think we're actually closing into an end of the first part. And next part is going to be about frequency space filters, which I'm going to talk about after the break. So I'd suggest we take a 10-minute break and come back 5 past 10. So see you later.